Okay, guys, so the next part of our lesson is on atomic radius, ionization energy, and so much more. So we are going to be looking at the periodic table and determining trends. So there are different properties of the elements that we can make trends on based off of the entire periodic table. So we can do what's called the group trends and the period trends. So the trends that go down and the trends that go across. So the first one we're going to start with is atomic radius. And so the atomic radius is a little bit fuzzy on an atom because atoms aren't like as perfect, like they're not just perfect circles with a nucleus and you can just measure the radius out. They are just fuzzier. So the way that we do this is we take two of the same atoms right here, two of the same atoms. We put them together and then we measure from both of their nucleuses, so nuclei to nuclei, and then if you take half of it, you have the radius, okay? So the radius is just 1/2 of the distance between the nuclei of two identical atoms that are bonded together. So let's look at how it varies throughout the periodic table. So the group trends are going to be the ones that are going up and down because groups are the columns and columns are up and down. Period trends are the ones going from side to side. Okay, so for atomic radius, the group trend is that it will increase as you go down. Okay, and just so you know, all of my arrows are going to be increasing arrows, meaning you are small at the top and big at the bottom, okay? So the atomic radius will increase as you go down a group due to the greater number of occupied energy levels. So you still need to know why on all of the trends. You need to know the trend, and then you need to know why that trend is doing that. So it will increase as you go down because if you look at if we consider lithium is on the second row, right? 1, 2, that's on the second row. So lithium has an electron configuration of 1s2, 2s1, okay? Well, now let's look at sodium. Sodium is on the third row, so its electron configuration will be 1s2, 2s2, 2p6, 3s1. So what we're comparing right here is the difference between 2s1 and 3s1. And so the reason that sodium is bigger is because 3 is bigger than 2, right? And this 3 represents what ring I'm on, okay? So that's like the third ring, whereas this one is the second ring, okay? So obviously the third one's going to be bigger, so we're going to increase as we go down. Okay, I'm going to erase all this so that I can talk about period trend. Okay, so the period trend over here, again, all of my arrows will increase. So you have to go to the left to get an increasing arrow. So it's small to the on the right side of the periodic table, and it's big on the left. So the reason for that is because let's compare neon and lithium. Okay, look at their electron configuration. Lithium is 1s2, 2s2. Why do I keep doing that? It's 2s1, I'm sorry. And neon is, man, I really am not doing great today. 1s2, 2s2, 2p6. So do you see how 2 is the outer shell for both of them? So both of them have 2 rings, okay? And so the difference between neon and lithium is that lithium only has 1 electron on that ring, and neon has all 8, okay? 1, 2, 3, 4, yeah, has all 8. However, lithium has an inner pull. So remember how the nucleus is pulling on the electrons? It has a pull from the 3 protons that are in it. Neon has a pull from all 10. So neon will pull heavier on this ring. So neon looks more like this when we draw it compared to lithium. Okay? It still has all of those electrons, and the electrons can still be on that second energy level, but the level is pulled tighter to it because the protons have a greater nuclear pull because there's just more protons. Okay, so just to kind of like finish that up, you take, for atomic radius, this is the size of the atom. You're going to increase as you go to the left and down. So the largest place is right here on the bottom left. Okay, so then just a little bit more information. It says that the period trend is less, so period trend is the one going across, is less pronounced at the bottom of the periodic table due to what's called shielding effect. So when you get down to the bottom of the table down here, okay, or down here, do you see how it's less, like it's more of a gradual change? You see how these are just kind of gradually getting bigger as I go across, whereas at the top they were just really tiny compared to really big. The reason that these are more gradual is this shielding effect. So what happens when we get all the way down to the bottom of the periodic table is we have, let me get some space to write. We have now added so many rings onto 1, 2, 3, 4, 5, 6, 7. We are so far out that these valence electrons at the outside have all of these other electrons shielding. Let me use a different color. So all of these other electrons are shielding the nucleus and the outer electrons from each other. So that is why that their increase in size is less significant. It still increases, but it just doesn't increase quite as drastically because of this shielding effect. So now let's practice. So it says, of the elements magnesium, chlorine, sodium, and phosphorus, which one has the largest atomic radius? And explain your answer in terms of the periodic table. So we are going to go to periodic table. We are going to locate all of these elements. So here's magnesium, chlorine, sulfur, phosphorus. Okay? We are going to remember our trend for atomic radius. It increases as you go to the left. It also increases as you go down. Okay? So this is radius. All right, so we can see that the small side is on the right and the big side is on the left. So we can obviously see that magnesium is the largest because it's on the big side. So we're going to go back, here, and say magnesium because because the atomic radius increases to the left. And now we need to put the following in increasing atomic radius. So increasing, the first thing I always do is write small on the left and big on the right so that I can remember that I need to go from small to big. So atomic radius, and we have bromine, cobalt, iron, and zinc. So let's go back to our periodic table. We are going to find, excuse me. We're done with those right now. We are going to find bromine, cobalt, iron, zinc. I don't know what else was on there. What else was there? Oh, and arsenic. And arsenic. And we need to put them in the order of small to big. So you're just going to follow this arrow right here. You're just going to follow the arrow, and you're going to say the smallest is bromine, arsenic, zinc, cobalt, iron. So you're going to say small to big. Put them in that order. I don't need to write it out. Bromine, arsenic, zinc, cobalt, iron. Okay, so that means that bromine is the smallest and iron is the biggest. Okay, so let's look at ionization energy. So before we understand ionization, we have to understand valence electrons. And I've kind of already told you about valence electrons in other videos and such, but now's the time for me to like officially teach it to you. So this is a term that you're going to need to know, valence electrons. Okay, so they are the electrons located in the outermost energy level. So that means that the N equals the greatest number. Remember, N is the number that comes in front of the S or the P or whatever. Okay, so to count the number of valence electrons in the electron configuration, you must look at the highest numbered energy level in the electron configuration and then add all the electrons there together. So let's look at potassium. Sorry. So here's the electron configuration for potassium. These are your energy levels. Okay, and then 4 is the highest one. So in the 4th energy level, all I have is an S1. And remember, this tells me number of electrons. So I have 1 valence electron. Let's look at cobalt. These are the energy levels, 1, 2, 3, 4, and 3. Again, the highest number, not the last one. So the highest number is 4, and this has an S2. So there are 2 valence electrons. Okay, there's an easy way of using the periodic table for this, so let me go show you that real quick before I forget. Let's get rid of all of our writing. Okay, so the easiest way with the periodic table is any of the D block or the F block, they are going to have as many as in the S orbital. So these will all have 2 from the filled S orbital. Because if I'm going into, let me use a brighter color. If I'm going into 3D right here, I've already gone through 4S. So 4 is now my greatest level. So all of these are going to have the S filled to get into the 3D. Same thing here. I'm going to have the 5S2 filled to get into the 4D. So it's just easiest to remember that these will have 2. These will have 2. Okay? And then all the other ones, it's just whatever group number I'm on. So the first row will have 1. The second column, the second column will have 2. The 13th column, however, will have 3. This will have 4, 5, 6, 7, 8. Okay? So that's the easiest way to remember it. It just goes 1, 2, 3, 4, 5, 6, 7, 8. And then in the middle, you just remember that all of these have 2 and all of these have 2. Okay, and these are valence electrons, and these are electrons on outermost energy level. They are responsible for all the bonding that happens. So let's talk about ionization energy, which it applies. So when an element loses or gains a valence electron, the outer ones, it becomes an ion. Okay, so we will refer to them as ions. The atom's ability to lose or gain an electron depends on how many electrons it has in its valence shell. If it has more than 4, then it is likely to gain the electrons to complete the valence shell. So let's talk about what it means to complete the valence shell. So if you noticed, I had 1, 2, 3, 4, 5, 6, 7, 8. Did you notice how 8 is as far up as we go? We always want to fill to 8. Okay? This is called the octet rule. Is that we want to fill to 8. So what this rule is saying, or what this right here, this bullet point is saying, is if the atom has 5, 6, or 7, it is going to gain however many it needs to get to 8. Because if it has 5 electrons, it can gain 1, 2, 3 to get to 8, rather than losing all 5. If it has 6 electrons, it can gain 1, 2 to get to 8, and 7 can gain 1. So they will gain electrons so that they can fill their valence shell. And if they gain electrons, they will have a negative charge. If it has less than 4, then they are likely to lose the electrons. So less than 4 is like the 1, the 2, the 3. So instead of gaining 1, 2, 3, 4, 5 electrons to get to 8, okay, it won't do all that. It will just lose all 3. So it will go backwards to get to the previous 8. Okay, so this second one, instead of gaining 1, 2, 3, 4, 5, 6 to get to 8, it will just lose 2. Okay, so always think which number is easier, gaining however many it needs or losing however many it needs. So if it loses those electrons, it will likely to have a positive charge. So when you look at your periodic table, the ion tendencies, so let me get rid of some of this. The ion tendencies for the main group elements, meaning we are not saying these, okay, not considering these. The main tendencies of group 1 is to lose 1 electron, so it will try to have a +1 charge. Group 2 will try to lose both of those electrons, so it will have a +2 charge. The purpose for that is if like beryllium loses 2, it goes backwards 2 places and becomes an 8, becomes a noble gas that's stable, okay? So group 3 will try to lose 3, so it will have a +3 charge. Now group 4 is dead in the center, so it can either lose 4 or it can gain 4 to get to 8. Now when we get to 5, we only need 3 more to get to 8, so it will try to gain 3, so that would give it a -3 charge. 6 is only 2 steps away from 8, so it will try to gain 2, which will give it a -2 charge. 7 is only 1 step away from 8, so it will try to gain 1 to get to the negative charge. To get a -1 charge to get to 8. And then again, 8 won't do anything, so it is happy. It does not want to ionize. Okay, so let's talk about ionization energy. Finally, I'm sorry, we had a lot to do to get around to it. So an ion is an atom or a group of bonded atoms that has a positive or negative charge. So an ion has an overall positive or negative charge. Any process that results in the formation of an ion is referred to as ionization. The energy required to remove 1 electron from a neutral atom is the ionization energy. This is specifically the first ionization because we're removing the first electron from a neutral atom. Okay? So you need to know the definition of ionization energy. So there, of course, is a group trend and a period trend with this. So the group trend is that it increases as you go up. So it would go up due to the top having a lower number of energy levels. So basically what this means is at the top we have like 2 energy levels versus down here where we have a lot. So it's a lot easier to remove this outer electron than to remove this one. Because, do you remember that shielding effect that I was talking about? The protons are trying their best to pull on this electron, but they have all this shielding in the way. Whereas over here, it's a lot closer, there's a lot less shielding. So it is harder to remove that electron, easier to remove this one. So the ionization energy is the energy required to remove that electron. So it is harder, easier at the bottom, harder to remove at the top. So the period trend increases as you go across a period, so that means that it's going to increase as you go from the left to the right, because as you go across, the nucleus does pull tighter. So as we go across, we're comparing something with 2 energy levels to 2 energy levels. And so they have the same shielding effect and they have the same distance, but the ones on the left side don't have as many protons pulling as the ones on the right. So the ones on the right just have a greater pull. So these electrons are harder to remove and these are easier. So this means that the periodic table trend for ionization energy increases as you go across and up, okay? So again, here's just some pictures to show you that lithium, it'd be more difficult to remove this electron because it's closer to the nucleus. And then over here we have, what is this? How come it's not on here? Hold on. It's cesium. So cesium, you have a lot of stuff in the way. So this nucleus is trying to pull in that electron as much as possible, but it has all these other electrons shielding it. So this one is easier to take away, so it has lower IE. Okay, it says consider two main group elements, A and B. Element A has a first ionization energy. So A has a first ionization energy of 419 kilojoules per mole. And B has an ionization energy of 1,000 kilojoules per mole. Says decide if each element is more likely to be in the S or the P block. So which one's in the S, which one's in the P block? Okay, so to do this, we have to look at our trend again. So our trend is going to increase as we go across. So this would be harder. So the energy would be more. So like IE would be so the ionization energy would be larger in the P block, okay? And it would be lower in the S block. So since B has a larger ionization energy, B is in the P block, and A must be in the S block because it has a lower ionization energy. All right, so the next one that we need to do, so we are going to move on to electron affinity. So electron affinity is the energy change that occurs when an electron is gained by a neutral atom. So we were talking about the electron being removed. Now we're talking about it gaining. But please notice that it's not energy required. It's energy change. So how much will the energy change if you add an electron? Okay, this is called electron affinity. We often refer to it as EA. So the group trend for this is that the electron affinity will increase as you go up and as you go across. So if you were looking at a periodic table, EA, electron affinity, will increase to the top right, okay? So the larger an atom's electron cloud is, the further away from its electrons, further away its outer electrons are from its nucleus. So the electron affinity is going to increase as it goes up. The larger an atom's electron cloud is, the further away it is. Okay, so on the bottom, the electron is the electron that you're adding in. So you're trying to take an electron and add it in. And on the bottom, it's further away from the nucleus, so it's more likely to be added. It's going to be at the top, you have less energy levels, and so the electron being added in has to be added closer to a nucleus than it does when it's further away. The electron affinity across the period, the electron affinity will generally increase as you go across because the increasing positive charge is the same sublevel attracts the electrons more strongly. So the same reason that we've talked about the period trend, we talk about how you have lower proton number and higher proton number as you go across, and that they're both on the same level. So over here as we go across, the higher proton level is going to be attracting electrons more. So the electron affinity is going to be higher as you go to the right because those more protons are pulling electrons in as much as possible. So affinity is the like, it's like it likes it or whatever. So the electrons are pulled, or like the affinity is like how much it wants to bring the electrons in. So the ones at the top right want to bring electrons in more. On the group is because the protons are not as shielded, so they're going to try to bring that electron in as much as possible. at the top than at the bottom where it just can't even try to reach that extra electron. Okay, and then as you go across, it's because you have more protons on the right side on the same energy level. Okay, ionic radius. First, we need to learn what a positive ion is called. It's a cation. I think of it as cat has a T, and a positive is a T-type symbol. So the formation of a cation is by the loss of one or more of the electrons. And so it always leads to a decrease in atomic radius. So this is something you need to know. The electron cloud will become smaller when you take an electron away. The reason for that is because the remaining electrons, the ones that are still on the atom, are drawn closer to the nucleus because you have an unbalanced positive charge now. So if you have a atom and you want to take that outer electron away, okay, this would make a positive, let's pretend like there's already one there. This would make a positive atom. So it will get smaller because once you take that electron away, now you have more positives than you have negatives. So it's going to increase, it's going to provide a very tight pull. So it will make it smaller. Okay. So, and then the negative ion is the opposite way. It's anion. I don't know how to remember that except I think of onion as negative, I guess. So onion, I don't know if that makes any sense to you, but it makes sense to me because and it looks like onion. Anyways, so anion is a negative ion. And so to make something negative, you have to add an electron. And so when you add an electron, you're going to increase the radius, which just makes sense. If you're adding electrons on the outside, you're going to make it bigger. But we can also compare the ionic radii of different ions. And so I guess what we just need to know is that on a periodic table, it goes across and down the same way, down and across. So it's going to increase as you get to the bottom. It's the same general reasons that we've had with the other atomic radius and not the ionic radius. Same general reasons, but they also follow the same trend. So the last one we're going to talk about is electronegativity. So electronegativity is in a bond. So you are looking at how many of the electrons that in one atom will pull towards itself in a bond. So the valence electrons hold atoms together in chemical bonds, okay? So if these are two atoms, the valence electrons are the ones that are holding them together. In many compounds, the negative charge of the valence electrons is concentrated closer to one atom. So basically that means that it looks more like this, where it's kind of all being pulled to one side. It's uneven. So the electronegativity is the measure of an element's ability to pull those electrons towards itself in a bond. So the electronegativities will increase as you go across, and they will increase as you go up, okay? So again, the periodic table for this looks like, if I can draw a periodic table, over and up, so top right. Okay, so out of these elements, gallium, bromine, calcium, which has the highest electronegativity? So we just go find these on the periodic table. Let me clear all this out. Okay, so like I said, it goes over and up. And so I believe it was gallium, bromine, and I don't remember the other one, and calcium. So we are comparing calcium, bromine, and gallium. Okay, well, according to the arrow, we have low to high. So if we're going to rank them in order, we would put calcium, gallium, and bromine, because calcium's on the low side and bromine's on the high side. So what that means is in a bond, bromine will pull the electrons toward itself a little bit more. Which one has the highest? We said it was calcium, gallium, bromine. with bromine being the highest. Okay, so let's just go back to the periodic table and do a quick run through because I know you're probably confused at this point. Once you put all the trends on your periodic table, it does get a little bit simpler. So the first one that we talked about was atomic radius. And atomic radius was just the size, basically. So the atomic radius is one of the only ones that goes towards the bottom left. Okay, so that's atomic radius. The next one we talked about was ionization energy. And this is the energy required to remove one electron. So this one went the opposite direction, so it went over to the top right. Okay. And then the next one we discussed was, let's go electron, let me spell that, electron affinity. Wow, cool. Okay, I wish it would stop doing that. Okay, electron affinity is the energy change to add one electron. So it also goes to the top right, so it goes up and over as well. Okay. So at the top right, we now have EA, and we also have IE, which is EA is electron affinity, IE is ionization energy. The bottom right, we have atomic radius. Okay, the next one we talked about was, need a new color, was ionic radius. And this is the size of ion. So we learned two things. We learned that cation is positive, and we learned that these are smaller than their neutral counterparts, neutral version. And then we learn anion, which is negative, and these are bigger than neutral version. We also learned a trend with this. We learned that it goes down and to the right, which is putting IR on this side. Then the very last thing that we talked about, I need a new color for this one, was negativity, if I can spell. Electronegativity. Okay. Okay, electronegativity is in a bond. How closely, or the ability, in a bond, the ability of an element to pull the electrons close. Okay, so the electronegativity also went to the top right. So I'm going to put EN. Okay, so that is all of them together. This is all you need to know, but you do need to review back over why the trends do this.